can you rotate your screen around so I can see what's going on? We're on. Okay. Hi everyone. Welcome to the Hive. This is normally an in-person experience, and we had to transition this very quickly, but we've done a lot of online streaming of presentations here from the Hive, so this is a little bit different from normal, but this is something that we're going to be doing a lot more of at this hour, and probably for the next few months, I guess. So our event today is 3 presenters, and what I might do is just say a few quick words about the Hive and the activities of this facility, and I might quickly mention the Curtin Institute for Computation as well, and then I'll hand across to Shambit Datta, who's just run off, but that's okay, he'll be back. So the Hive is the university's visualisation facility, and our role is to support and encourage the use of visualisation technologies in research projects across the university. And there is a range of visualisation activities in the 3 presentations we'll have today. The Curtin Institute for Computation is a large group of academics right across Curtin University, and our role is to I'm a member of the CIC, as many academics are, including Shambit, and the role there is to promote the possibilities and the options of data science, basically. So at this point, I'll hand across to Shambit, who will introduce the speakers. Thank you, Shambit.
Thank you, Andrew. Can you hear me?
Oh, I can.
Excellent. I think Rob is getting some feedback, so we might have to switch off the Hive microphone. Are you okay with that, Rob?
Maybe he's already turned it off. Anyway, you speak now, Shambit, and we'll continue.
Tomorrow. But I thank you all for being patient and logging in. The idea of this workshop really, the genesis was around a visit by Professor Robert Woodbury, who was also my PhD supervisor many years ago. And he was doing a grey nomad trip around Australia, so we invited him to join us. So the idea is, Professor Yasushi Ikeda is, of course, a very well-known colleague, and he was also planning to travel to Australia at some point in time, and when he heard that Professor Woodbury was visiting Perth, he said, I will make my visit at the same time. And of course, at that point I thought, we need to have the presence of Professor Tom Cavan, who's also one of the pioneers of our community. And he readily agreed. For various reasons, he's unable to be here today, but he's with us online. The basic tenet of this workshop is really an interactive format. We're trying to bring together design and data science. And these 2 disparate disciplines really have been working together for a long period of time, as the 3 talks today will show us in action, to address user needs and solve really critical interdisciplinary problems. So we have 3 leading academics. I will introduce each one of them first to you, and then we will go on to each of the lectures and possibly have, if there is time, question-answer discussion. So Professor Robert Woodbury will present today visual exploration of design alternatives, his new system which is called D-Star, and it's a very interesting one in that it combines an interactive design gallery with designer-directed making. Professor Woodbury is, of course, at the School of Interactive Arts and Technology at Simon Fraser University, the founding chair of the graduate program there. He was also the scientific director of the Canadian Design Research Network. That is the National Association of Design Researchers in Canada. Professor Ikeda is from Keio University in Japan, and he's a professor at the Graduate School of Media and Governance at Keio. And he graduated from the University of Tokyo. He has worked with Maki and Associates for a long period of time. And he has also been involved in recent design projects such as the Taipei Main Station. Will present on digital construction technology, three-dimensional construction guidance, construction robotics, non-standardized component production, IoT. Finally, Professor Tom Kavan will talk about smart cities, and particularly the project that he's been working on, harvesting high-quality data from sensors embedded in urban infrastructure, can inform planning and design. To some extent, he will share the results of a living campus experiment at the University of Melbourne, and he will Tom is very well known, of course, in Australia. Needs no introduction. He was Pro-Vice Chancellor of Campus and Global Development at the University of Melbourne. And he has been instrumental in the establishment of the Melbourne School of Design, as well as the award-winning building that hosts the school. His most recent book is The Making of Hong Kong. It explores volumetric city form, sustainable urban solution. So I guess that's a very quick introduction to all three. And without further ado, I'll hand over to Rob to talk about the STAR visual exploration of design alternatives. Rob, are you there?
I am in there. I'm now speaking. Can people hear me? Because the channel is completely garbled from my end, and I'm getting feedback from Central. So now I can barely even hear myself. The channel is completely garbled from my end, and I'm getting feedback from Central. So now I can barely even hear myself. The channel is completely garbled from my end. So there is about a 1 to 2 second delay in my voice coming back to me. So there's about a 1 to 2 second delay. Is that any better?
Can you talk to him and say, can you YouTube it? Just talk.
Can you wave your hand if you can hear this clearly?
Yeah, just put them
What I'm going to do is mute my speaker itself. So unfortunately, I won't be able to hear anything that anybody wants to say. So use the chat if you really need to get in touch with me. Oh, and Tom tells me turn off the sound on YouTube. And bye. I believe I've done now, but it's going to work best if my speakers stay muted. So we'll go from here into sharing my presentation. Okay, I'm now sharing Microsoft PowerPoint. Shamik, wait if you can see things on your screen. I'm here today to talk about the latest stage in my very long-standing work on design space exploration. But it's a stage that has really changed my thinking because it's led me to focusing in quite a different direction than I focused on for the last 30 years. An aim at an interface design that's radically different from certainly anything I've thought about And hopefully I can persuade you that it's radically different from anything else out there at this point. And I call this talk Dialogue plus Exploration. It's a combination of these two well-known theories in design that's led me to this new interface design for working with design alternatives and exploring design spaces. So I'm going to start by showing you a video of the new D-Star system. And this is a foreshadow. You'll see it, and then I'll explain why it's the way it is, and then we'll see it again right at the end. I'll stop it maybe once or twice as we go along. For those who don't know design, this is the Grasshopper parametric modeling system. It's like most parametric modeling systems. It maintains a data flow graph on the bottom, which is a logical expression of some kind of model, and an image that represents the current state of the model on the top. Star, which is sitting on the right-hand side of the screen, enables us to take alternatives created in Grasshopper and store them onto a web interface in objects we call collections. Collections enable the organization of work. You can have multiple views of collections, and you see two here, in which these two views, one is the collection in a folder view and one is a parallel view, are representations of the same collection. We provide a number of operations in D-Star directly to make new alternatives without going back to the modeler. Further, we can edit alternatives in place, multiple alternatives at the same time, and multiple parameters. And we can combine alternatives with operations we call like the Cartesian product, that enable us to mix together alternatives dynamically without ever actually having them modeled in the modeler. And the alternatives in D-Star are live. They can go back to the modeler anytime. And the underlying math and computer or system design of D-Star enables this to potentially be used with any parametric modeler, including the architectural modelers, and for instance, we can use them with Excel. Okay. D-Star is the result of combining two theories. The first theory has a name, it's called HIPS. The second theory doesn't really. I've labeled them Theory A and Theory B. The essence of Theory A is that to design, to explore design space. What is this thing we call design space? It is an array or a network of designs that is developed progressively by visiting one or more designs, doing something to them, to create a new design. Informally, we work with design space ideas all the time. We brainstorm, mediate, we have options, alternatives, variations, and versions. We often say there is more than one solution. I can ask you what other verbs or nouns can be here that in the common vernacular explain and refer to design space. Design space labels a theory, Newell and Simon's HIPS. Human information processing theory. The labels a theory with great predictive power. It's probably the theory of what's happening with people design that gives us the greatest predictive power. It tells us lots of things about how designers work, but it's incomplete. It's incomplete because this slide is entirely compatible with Theory A, the HIPS theory. It depicts a white man casually leaning back in a chair, an empty table, looking at three highly developed alternatives. Okay, this is caricature, and I'm taking something out of context, but that's fair game. But contrasted with this slide, I think everybody would agree that this is closer to reality than how. The first, and if this was an interactive audience, I'd be asking you, and you'd be giving me all sorts of interesting responses. But among the responses I've heard, the designer is leaning in. He's engaged. He's got multiple media at hand, in this case, paper, multiple pencils, scissors, and fabric. He is a fabric designer. Designs are arrayed, they're juxtaposed with each other, and they can be moved around easily because the pieces of paper aren't bound together. And sociologically, it's close to reality, because the majority of people who are studying designs right now are female. So there are some invariants here. The invariants that differ from theory A are picked up in theory B, which says that to design is to dialogue through medium. There have been many authors for a long time advocating versions of theory B. C. Suchman's Situated Action, Edwin Hutchins' Cognition in the Wild, Gabriella Goldsmith, The Dialectics of Sketching, Donald Schoen, the reflective practitioner, are all, in my view, variants of theory B. It basically says design is the dialogue through medium. And the dialogue happens with yourself, with others. The core of the idea is that there's this very tight cycle happening between whatever is being put into the medium and whatever you're thinking. If your thinking is influenced by the medium, your actions are influenced by your thinking, and this goes on in a very tight and immediate cycle. Much of it is tacit, that is not accessible to conscious cognition, and it's so engaged that one doesn't stop to think about abstract things like unfolding or exploring design spaces. So the insight I've come up with is that we want the immediacy of theory B, the predictive power of theory A. The insight I've come up with is that dialogue induces design space. It's that by the action in a medium in which you are directly engaged with the objects at hand, the designs you're creating, you should be able to rely on a system to induce the design space that it's developing or it's recording for you. So if we take that seriously, then we say, well, what do designers do when they're in design dialogue? Well, the literature tells us that they mostly sketch. But most of the literature takes us down a bit of a rabbit hole in what is sketching. Until Bill Buxton came along in his beautiful book, Sketching User Interfaces, and gave a functional definition for sketching. And that functional definition isn't bound to the 2B pencil or the 2B paper. Rather, it describes sketches by what they do for people, by the amount of commitment they have, and by the speed with which we create them. So designers make things in design space as they sketch. What are these things? Design alternatives. Now, I know there's lots of terms in design literature. I won't argue about the validity of such terms: variations, alternatives, versions, options. I use design alternatives in all my work as a generic and hopefully pretty neutral term. Let's look at some design alternatives. Here's a very old sketch. It's a Leonardo da Vinci sketch. I think you can argue that there are alternatives somehow stored in this sketch. 3 places: the horseman's head, the horse's rear hooves, and the horse's front hooves. Now these alternatives, they exist as multiple positions of the hooves or the head. They're not definitive gestures towards something that may or may not be in the final sculpture. Rather, they're ways of feeling one's way forward towards the form. Nonetheless, this shows that in a single sketch, you can express multiple directions of thought and multiple alternatives. Industrial designers are trained to juxtapose sketches. A typical sketch may be polished a little bit, public consumption, but surprisingly not polished much. It's a sketch of alternatives done at a stage that industrial designers call ideation. And a skilled industrial designer invests somewhere between 20 minutes to an hour on this sheet. Definitely no more than an hour. And in that very short period of time, you can produce at this high level of resolution multiple ideas that help them advance their thinking towards the forms of which they will ultimately arrive. And there's the archetypal back of the napkin doodle. It's a doodle Philip Stark somewhat apocryphally made on a napkin in a bistro in Italy that led him to the combination of multiple ideas that expressed a spaceship and a squid that functionally, or more or less functionally, made a lemon squeezer. Often, designers work in media in physical and digital mixed media. These are actual maquettes models that were created in the process of designing the new elephant house at the Copenhagen Zoo by Grady Peters at Bureau Happel, and then he moved to Foster Partners and was immediately given the job of finishing the project. In this, you can see multiple ideas, none of which actually occurred. The final result in the form they're expressed in here. And we see throughout the literature grammar-like displays in which multiple ways of unfolding an idea are shown in a single display or on a single sheet. In this case, multiple ways of achieving Celtic knot. And note that books like this were published widely in the 19th century. Current parametric modeling systems have created the gallery trope, in which we make a display of an arrangement of variations of a single model. In this case, one created by Nagni Shireen for a PhD study in what do people do when they have 1,000 such models or images to work with. Parametric models themselves embody infinite alternatives. In this case, this is a single parametric model that through changing the input points, or actually changing the input points, can yield an infinity of multiple Bezier curves. And so parametric models as a medium give us the feature that they can apply infinity, but they're limited to display at one at a time. Even in computer programming itself, people claim to functionally sketch with code. This, by the way, is the geometry that Peters arrived at for the new elephant house. It's turning the top of two intersecting tori. So I think I've demonstrated that the reality of an alternative depends upon the design medium used. A corollary here, for any of the old fogey design theorists in the room like me, is you have to be very careful in reading the qualities of a sketch, what the qualities of a sketch should be in a new medium, and trying to transfer the qualities of a pencil sketch into that medium. There's lots of tigers lurking in the intellectual long grass when you try to do that. But an important point is designers work with such alternatives directly. They're engaged with what they're doing, and they're not thinking about design space as they work. This is the essence of design dialogue. A direct interaction with the alternatives, and it's the responsibility of the system to induce the exploration. So what I'm interested in is directly interactive design space exploration, where the interactions are immediate, direct, draw you in, to sketch, to functionally sketch. That is to make lots of things very, very quickly. Well, we've had design space exploration for a very long time. My colleagues, Reinhard Koenig and Gerhard Schmitz, worked from 2016 doing alternative layouts for city blocks where they used self-directed maps, self-configuring maps to sample a design space and create a large design space of alternatives automatically and present back to you some kind of display where you were free then to look at the display and to choose the one you wanted to go forward with. But that was the level of interaction. So we've had such exploration for a long time. We've also had interactive exploration for almost a longer time. This is a re-implementation of Richard Dawkins' 1986 design space exploration program. It was an evolutionary algorithm in which the user played the role of the fitness function. So at any point in time, one alternative instance from by the EA was put at the center. Variants in the next generation were displayed around the periphery. The user's role was to pick the variant that they wanted to bring to the center to provide the genotype that went forward to the next generation. This program has been re-implemented several times, and it's actually a lot of fun to play with. You can get from the bug to the Medusa in a surprisingly small number of steps. Then there is directly interactive design space exploration, which has some very, very different features. I'm going to change the sharing here. Hopefully, it works. So we should be seeing now sharing in the web browser. One second. Ahmed, you see the web browser? Wave your hand. I hear you. Thank you. Okay. This is a very simple design space explorer. The representation over which it is operating are simply graphical trees. But it has some interesting features. First of all, the objects that you see below in the snapshots are live, in that I can bring them back and forth into the live editing part of the interface at any time. I can have multiple alternatives clicked as linked, and when I edit those alternatives, they edit together. So I'm working with the alternatives directly, and I can clone things and change those alternatives. I can add snapshots where I am now. And so you get a sense that there's a very rapid exploration of ideas from a single tree. All of the things you're seeing, I did in less than a minute, starting from a single tree when I was preparing this talk. I'm going to share back PowerPoint. And PowerPoint should now be back, right, Shonda? Raise your hand. Okay. So the idea is to find ways to directly interact with one or more alternatives at the same time. Why interact? Why not just generate the entire space, select from it? The answer is that you can't. Design spaces are vast. How big is the problem space? Consider Jorge Luis Borges' library of Babel, which is a library of all possible 410-page books. It has in it approximately 2 times 10 to the 2 million possibilities. A pretty big number. Certainly, exhaustive enumeration is not a feasible strategy. Nor would I argue is any sort of representative sampling, even though that is the direction most of the literature takes. Throughout all of this, I think I've built the argument, Hutchins' argument, not mine, that the tool plus people is the cognitive system. By introducing new forms of design media, you change the cognitive system so that the overall behavior of the cognitive system changes so much that it's hard to predict prior medium what you should do. So when one embarks on trying to design a new medium, you shouldn't expect a whole lot of guidance from prior things like sketching on paper. Now, we can change the tool. We can't really change human cognition. But people do adapt their behavior and change their behavior in the tool because the tool plus the brain. Change the tool plus the same brain creates a new cognitive system. The problem is, most design studies have been done with manual media, primarily pencil sketches. So very few studies exist on how digital media affect design, process, and outcome. Homer Aiken, who sadly passed away last week, argues that cognition varies across design domains and problem types. He's silent on media. Goldschmidt describes how designers use sketches. All of our studies are done with now very, very familiar sketches. In contrast, studies done in the digital domain, with the exception of some stuff in the last 10 years, some pretty brilliant stuff, is flawed by a key assumption. Presume the single-state document model. Michael Terry defined as requires a document to be in one and only one state at a particular time, thereby imposing a serial linear progression for a task that it decides a messy, highly iterative creative process. I'll give some examples. On the left is a shot from the full Form Z modeler, which is still being used, and which limits you to a single display of a single model at a time. On the right is something almost as bad. It's a shot from Grasshopper that gives you a single display of a model plus one instance of the model that can be up from the infinite number of instances that can be created by changing parameter settings. So that particular, going back to the single state document model, pause and reflect. Ask yourself, what tool you use doesn't have the single state document model as an overpowering assumption in its interface. Second, you have to get around it. For example, to make a version in Grasshopper or a scenario in Excel. How do you do it? I know the answers to those questions, right? Vanishingly small for the first one, there aren't really tools. And I'd be delighted to be shown wrong. And the second one is, the typical answer is with a great deal of pain. So, Design Space Explorer then is a toolkit. It comprises tools to understand, navigate in, and extend design spaces. It must work through immediate engagement with the alternatives themselves, more than with an abstract notion of the design spaces being generated. And conceptually, it must be multi-state. People have built lots of explorers, some with higher levels of interaction than others, but no single model for these yet dominates. I'll start by showing the single state model. Single state explorer. It's supposed to, oh darn, the video on this one isn't working. Genesis would show you a Queen Anne house being developed automatically by the Explorer in more or less real time. And it was a single state explorer developed in the late 1980s. They've been using a rule-based system operating over solid objects. And it enabled very limited exploration, but explicit exploration of the tree as their result. Here is a very commonly used prototype tool today from Thornton Tomasetti that allows you to take a set of things that have been pre-generated and basically filter them. So here we will see being filtered. There's the set. By applying brushes that narrow the set down, you can see subsets of the objects that have been pre-computed. There's no ability to make new objects. It's strictly a one-way street from generation to visualization. Cambria developed in our lab, developed the notion of collections, which is that as designers work, they want to organize their work into groups of things. Not the 1,000 things they have created in this section of exploration. The group of things they're interested in today, the group of things they want to show Sean or Nikita tomorrow, and the group of things that are serious consideration as alternatives going forward in the project. So, how then do we make these design space explorers? I've argued we don't have much guidance in the literature. We certainly can't copy our medium. There are sort of general frameworks, but they're nearly vacuous. This is Ben Schneiderman et al.'s framework from 2002. It really kind of hasn't been improved upon. I'm sure you would agree with every one of those statements. I'm sure equally that few people would have much of an idea of how to implement them. So the current frameworks aren't actionable. There are some very good cases. The recommendations follow from the cases and are not general arguments. Here's one such case. This was Bjorn Hardman's juxtaposed, in which he supported interacting not with one, but many alternatives at the same time through an idea of parallel editing. Now, the idea there is that a human visual system is much faster at scanning than the human brain is at thinking. And it can detect points of interest in multiple alternatives simultaneously faster than you could by looking at them one at a time. Gemini, which does parallel editing, it basically implements parallel editing over a parametric model lookalike called node balls, like cloning node balls. I hope there's no sound with this. The sound is embarrassing. So, the point here is you can see that the interface is very complicated. That's partly my fault. I didn't insist on simplicity as a supervisor. But it's pretty clear to me that an interface for effective design space exploration has to be way simpler than this one symbolically for us to use it, or else the designer just gets buried in the interface. One of the first things that I would drop, in fact, we have dropped, is multiple simultaneous visualizations of the data flow graph. I don't think there's a whole lot of mileage in that. And Partech put together user-defined collections and did a number of things with them. You can see Partech is plugged into Grasshopper, embedded pretty deeply in Grasshopper that has multiple collections. From any alternative, you can enter and edit things in Grasshopper directly. Send them back to the collections. Things by copy and paste or by drag and drop, collection to collection. I'll go back many years to Mark Tapia's gedit, which is in many ways an archetypal grammar interface. And it required you to explicitly manage a grammar set, choose which rules apply, choose which objects on which to apply them. And exploration became a fairly cerebral process, where one literally did sit back and think slowly about what you were doing. That's not where I believe you need to be. Now, there are some good cases and bad cases. I give sincere apologies to any machine learning people in the room, because you're a bad case. But your work is actually essential to this going forward, this whole agenda going forward, with one important caveat. So, I call this bad case the fallacy of appealing to an oracle. Where you set up some kind of automatic process, let the process run, and then reduce the task of the user or designer sampling from the results of the process. Do not to discourage inquiry about how the process works. Most published research on design space exploration takes this form. The most cited such paper being Joe Marks et al.'s, it's Handelman et al.'s Design Gallery, which was published in SIGGRAPH in 1997, in which a design model is considered a multifunction black box. There's a sampling process that gets a representative sample from the parameter settings of the black box and arrays them for choice by the user. So that's an archetypal demonstration of appeal to an oracle. There's no way the process goes forward beyond selection. Not in any way to denigrate such work. In fact, the oracles, the automatic algorithms, are essential for design space exploration to go forward. But they get in the way of trying to figure out how to interact directly with design spaces. To the point where in our lab, my students are not even allowed to try to program an oracle, except as a little finger exercise, because it's so easy. It distracts them from the hard work that we're trying to accomplish in direct interaction. So, direct interaction, we Around the fallacy of appealing to an oracle. Designers devise things to achieve goals. Goals keep changing. The task of designing a design's role is to be critiqued and reworked. So, to defeat the fallacy of an oracle, you build a feedback loop into the system, and you make the oracle transparent. John argues this invariant thoroughly. Again, his work on the reflective practitioner in the cases he documented shows this. Oracular results, no matter where they come from, initiate yet more design work. Radner et al. Pointed out in a study of multiple simulation people and optimization experts, the computed optimum was often used as the starting point for further work, not as the end product. I think I stand on pretty good ground saying a system provides starting points for further design. The implication for system design is we've got to have interaction, hooks or operations all the way down to the bottom. So to return utility to these literally hundreds or thousands of papers to design space exploration by invoking an oracle, if we can build an interaction layer for such oracles and hooks for direct designer interaction over them, close an important loop and make that whole body of work more useful for designers. So then my task becomes designing directly interactive design space explorers. You have confidence in a bunch of features at this point. Coordinating multiple views will be familiar to probably everyone in the room, where in one view, selecting something in one view selects the corresponding objects in other views. Juxtaposition, or putting things side by side. This was the first version of our design gallery system in 2016, in which we had user-definable layouts of juxtaposed views. Superposition, this is a Majeka's paper from 2018, is a very powerful strategy, but only in domains in which objects can be superimposed. It doesn't often happen in buildings. In carefully chosen case, it happens a lot because the things that are superimposed are 64,000 variants of desk support structures. You're seeing a cloud of these things, and their tools selecting them based upon selection or carving away or negative selection of parts of the cluster of support structures. Superposition is generally not a good strategy for architecture because too many things lie on top of too many other things. However, it can be used. Here is a parametric model output of a very abstract model, and it's 2,048 variations, very, very quickly displayed simultaneously. And when you click to stop, the thing you're interested in is in the last second or two of that video. It turns out that you can actually detect interest in seeing something for a relatively small fraction of a second. And you might not think this is a serious proposition for an interface, but it is. In fact, it's the most common design space exploration interface in existence today. Many games of design space explorers for outfitting armor or car properties based upon rapid serial superposition. In abstract designs, on the left you see a set of designs. As images, on the right you see abstraction of them as a small multiple sprite. User-defined collections are absolutely essential. When you're exploring designs interactively, you generate lots of them, and you need ways to organize them together. And some of these collections can be smart in that they can be things like history trees, but a lot of them just have to be what the user decides to put in a particular collection. On the left, you see user-defined collections from Artec. On the right, you see a hypothetical design done by one of our undergraduates for a lot of interactions with user-defined collections. You should be able to edit in parallel, in this case with parallel coordinates, editing of two alternatives yields other alternatives shown on the right, and in the little wheels on the left, A and B, those alternatives are being computed just after a move. The class of operator is called design hysteresis, which says you can take two or more things you've already created. In fact, you can create one or more, take one or more things, and find around it things you might have created with a little more work. In this case, it's a Cartesian product of the two checked alternatives, producing a whole range of other alternatives. You can implement design hysteresis in a wide variety of interfaces. In this case, we're showing two alternatives in parallel coordinates combined into multiple new alternatives. Finally, an overall pattern is that in any such interfaces, the inputs to a model, the gallery propose alternatives, and the outputs dispose. So in this diagram, the curved sketch through inputs generates a new alternative. A similar sketch for outputs would generate a target for optimization, basically a target for an interactive oracle. So here are some interface designs we've already come up with. Design Gallery 1 presented its Smart Geometry 2016, juxtaposed design alternatives that worked with Dynamo, generative components, and Grasshopper all simultaneously. Artec built inside Grasshopper, Design Space Explorer with several of the properties, including design hysteresis, user-generated collections, and parallel editing. And Explore is a fanciful, there's nothing behind it. It's an undergraduate project that gives different ways of zooming in, interacting with selecting, selecting parametric or alternatives, making new collections from them, displaying them as things analogous to word clouds, semantically zooming. So showing an interface designer these ideas, they do come up with interesting things. Going from those things to an implementation ends up being still a fair amount of work. The work that we have right now is the D-Star system, which I'll play you again. I'm a parametric modeler, multiple user-defined collections. User-defined collections are the primary objects of the interface. It's easier to make collections than it is to make alternatives. Collections can exist in multiple coordinated views. Views can be different. You can sketch new alternatives, based upon old alternatives. You can do parallel editing on multiple alternatives. Many, many different ways in the current version of the system. You can do design hysteresis. In this view, in this version, let's go forward here. Do design hysteresis, this version by selecting two alternatives and some of their input parameters, generating a space. Alternatives made by combining all values of the input parameters in both alternatives together. And we can restore things back to the modeler, linking the modeler and alternatives into the cycle of design dialogue. Now, in doing this, there remain no general models. There are no Kuhnian paradigms at this point. In fact, I believe we've invented something quite new, different. We don't really know anything about whether it's the best one. We do know from a study of about interviews with about 30 expert designers, people find it very appealing and want to work with it. So for now, research like this will proceed by cases, design, implement, and evaluate them, seek new and refined features and supported arguments. It's fundamentally a creative exercise, especially to the graduate students in the audience. It falls right into Sadelmeyer and all's InfoVis methodology at the core stages. What we're trying to do is to characterize the problem, abstractions needed to solve it, and create prototypes that capture these things. Utility lies in the characterization of designs, directly interact with explorers, or establishment of requirements for future work, to a lesser extent, validation of prototypes. Methods for this are mostly qualitative. Quantitative studies, and we've designed a whole bunch of them, are unconvincing at this stage. The qualitative studies tell us how people use the systems, and how they connect back to creative work in ways that help us go forward. This talk is, of course, only part of the enterprise. Representations for alternatives are another task. There's a lot of work, for example, to do getting a single parametric model to represent multiple alternatives directly in the model. Although Gunther in 2016 in his thesis gave a good idea for how that could be done. Finally, I'm not alone. The Tanos economy from Georgia Tech has built many of these principles directly into its latest shape parameter interpreter, which no longer feels like that old copy of shape parameter interpreter. It's beginning to feel like a design dialogue system. There are dozens of videos at shape.design.gatech.edu. So finally, thank you very much.
Thank you, Rob, for that presentation. I'm just grabbing the mic before I hand it to Professor. Presentation. I'm just going to say very little, except that Professor Yasushi Ikeda will now show us his work in the Ikeda Laboratory at Keio University, how he is using design and data science. Thank you. Sushi.
You guys hear me? Let me check. You guys hear me? Let me share my presentation firstly. Sorry. Right. I hope you guys are seeing my picture presentation, right? The sushi picture. Just because I want to let you remember my name, the sushi is an easiest name to remember as a Japanese because you just put the sushi. It's really an honor for me to have a presentation in this international workshop in the middle of two distinguished pioneers and the leader of the digital design, Professor Berlin and Professor Thomas Kamal. Anyway, I'm in the room of the Western Pass. And, I'm really appreciating all of the effort the organizer made under such stable circumstances. And, of course, it's a bit tough to have a presentation in the middle of two super great professors. And I'm already overwhelmed by such a phenomenal and brain-blowing presentation by Professor Berry. But since it's my role, I have to do it. And let me introduce myself quickly. I'm also practicing an architect in Japan in the past 30 years and teaching Keio University Graduate School for Media and Governance. And around the same area. And these are my practicing work. And, I did much practicing, including some international work, such as the Taipei main station, Taiwan. But my career goes back to the beginning, 30 years ago, with Professor Maki, who is my mentor, and also my supervisor in University of Tokyo. In the time that we are using a computer like this, but I have a chance to help him with using computational simple geometry by coding. Then I have a chance to be hired by Mr. This. That was in the beginning of the career as a result. Started in 1987. But, as an architect, My concern about digital design is a little more in construction technology. Many aspects, I think, in architecture technology has been matter of geometry. It is not only mathematical definition of the shapes, forms, and the spaces, but also it and the functional tool to identify the performance of these properties. So this is one of the practical work I did. It's showing kind of structure of small house. It's called bamboo bush structure. Basically, to achieve it's a randomized pattern of structure. This randomized pattern it needs to be built by some simple modularize the unit because the fabricator required has to do it. Now that is one of them, but anyway, with these experience, and we started thinking a kind of method to specify an appropriate randomness for the fabricators. Similar to this, we can create a kind of heterogeneous patterns that can keep certain performance through algorithmic process. This is the also pseudo-random pattern to create irregular uniformity. Using the two different types of the unit. It follows an idea of the so-called Penrose pattern by Roger Penrose. In both of the cases, I'd like to emphasize these units and the patterns are part of structure. So basically, again, I am interested in how these ways are be applied to the construction technologies. And fortunately, I have a chance to teaching at the university, and the Japanese university system allows us to have a so-called laboratory. Our laboratory now are doing we call it an architectural mathematics, which like today. My concern these systematic construction and the sustainable design technology. This is the actually our see that quickly showing the video for which our laboratory works.
Society is undergoing significant change with the advance of technology. Architecture and cities are indeed moving forward into the next step. Everyone can participate in cutting-edge manufacturing. By visualizing unperceivable problems, the way of manufacturing will change. Everything is connected via the internet. Mixed reality is around us. How will technology change the world? Even with the realization of innovative spatial design and manufacturing techniques, the way human thinks and uses space does not change. We create a new form of relationship between information technology, space, and manufacturing, expanding the spectrum of technology. As digital fabrication spreads further to people, democratization of manufacturing enables everyone to make free forms everywhere. The collaboration of robots and human labor not just makes the process of manufacturing safer, also makes it more interesting. By visualizing complicated problems in an intuitive way, it becomes possible to create an environment where space by deepening the understanding of human. It will be possible to create a space that effectively supports human activities. By digitizing design information such as disciplinary also becomes possible. By performing 3D scan, such as photogrammetry, you will be able to create a digital adjustable model that allows you to modulate the shape and make it 3D design. For example, when there is a language barrier, digital model makes cross-nation collaboration feasible. Control of machine and environmental simulation is possible. Sharing of digital model, the intervention of robots for third parties is now a reality. Cross-disciplinary creation also becomes possible. As information becomes the center of society today, practice of architecture is also required to be computerized.
There's almost everything, but maybe I will spend a little more time with that, our history. We joined actually the Smart Digital Workshop in 2010, which Professor Corona was the first attempt of the digital communication workshop. It's become turning point for me as well. There is not much to say about the normal freedom to be created by military integration tools, computer monitor. But following that normal manufacture of genitals presented by data and productivity materialization on the board, radically in many cases. That is, I think, for us, it's very important. And right after I come back from Barcelona, we bought the laser tele and start testing here. It is in 2010, as the same year, a laboratory team arranged the experimental project to investigate and demonstrate the potential of digital geometry, digital communication. It's called some porous film. The basically our intention of this project was to achieve shape with the double curvatures, the simple joint using the panels, and the cross with curvature surface is a typical motif for computational geometry. However, the type of the surface needs to be assembled with the discrete parts. It is almost inevitable to divide it into the architectural. So it is, again, interesting point for us. And one more thing is it can be assembled without nails and the screw and the groove, thanks to the fabrication method such as the laser cutters. Does not affect the product as long as the process time change right. However, phonic performance very sensitive. It could be many different ways to subdivide the geometry. As there were significant differences in the vastness and the precision of the construction. In other words, algorithm to create a series of unique parts is a primary matter of the geometry and the productivity. This specific case, you can see it as a kind of, but this finger joint can be parametrically modified following each shape. That means that this effortless assembling achieved by is parametrically generated joint details. Then see the non-standard homogeneity as enabled this construction and the irregular form with a relatively simple part. Used to be, we just think panelize this kind of non-rectangular shape, divided into the rectangular panel, and just accept a kind of visual R in the peripheral. However, currently, it is much easier to divide it into something like this. First, we have a way to make this coordination. So, rather than equalized parts, we are more into the coordinate panelization. Therefore, the technology of modern architecture can be examined, I think, in terms of these basic promises of the digital age. Then as I can go back to something like families, the universal space. Industrial technology has an economic potential to increase in the productivity regarding the performance, predictability, based on the regularity of material behavior. That is why the materiality and the standardized use of the identical unit. This economical point has been pursued while the industrial civilization led in globally. With the methodology based on the concept of standardization. Position from the parts to whole can be optimized with the repeated arrangement of regular unit. In other words, the rectangle is the most efficient types of the shape to construct building with identical parts. Orthogonal geometry can maximize the advantage of mass production industry by minimizing the cost of manufacturing because rectangular is the most efficient shape of construction using an identical part. I think that is why modern maestro architects and the lawyer advocated the use of rectangular parts in orthogonal coordination geometry as a symbolic feature of the universal space, the age of the popularized and industrialized. That's why we have been trying to explore some other way to use a digital geometry for designing communication construction using this non-standardized through the data. We may think this process could be a kind of tectonic optimization. In this specific case, we just try to make arbitrary shape from originally just the shape of the human being, translated into the loop of the Voronoi cell panel, and which automatically transfer to the certain ways to build it. As far as the way to make this good, any kind of shape can be achieved by the same idea. So we also bring this idea to the a bit more practical application. In this case, this is the Japanese fast CLT structure house responded to the expectation from the first three of Japanese cedar using a CLT cross laminated panel structure. In this case, it's very important to have many alternatives, as Professor Woodbury told us. In our case, also, since this is a kind of prototype of the house, for us it is very important to show how same idea of the construction technology can apply to the many various different types of the house, after keeping joint detail or way of construction the same way. So this is the idea that the shape of the panels provided directly by the certain parametrical way, that we don't need to care about the difference of joint detail or other construction issues rather than the shape of the house itself. Basically, it was built in 2009. Let me summarize things I have so far. I think technology and design are a kind of relationship between program and activity in a space from the social demand, the potential this prediction in the material and construction. So design is always a kind of discovery, development relationship. Used to be we just think that this will start in a shape or figure, so we call it maybe tachi in Japanese is representing. In the background of the katachi, we should have some idea of the model, the pattern or style, which can write these shape parametrically. However, it's a kind of common ground of transformed material. However, by using an information technology, as Professor Woodbury have already mentioned, it's become more easy and more systematic, and our design got to that method, method system, without not only the Katachi. So from design to Katachi to design to Shikumi must be the one big trend. There are other inspirations from the potential of these ideas with the irregular uniformity coming out, rising from one particular practical project I did in a local city in China. Project was built in 2011 as a Japanese-style hot spring super, a remote village in northeast China. Is a contemporary technology, no skilled craftsmanship or enough available. You can see there how people working on the site. We noticed local craftsmanship, the traditional stone finish in the bottom left. These are kind of performance and amateur builders, but because of these irregular units, as it's irregular, it's more easy to hide the and mistakes of these. This is very interesting that it is very handmade finish by hiding an irregular gap between parts. So we apply this idea to the other part of the project. Is this seeding pattern of the rulers. Well, to keep the allowance for error and sufficient accuracy in architectural finish would not be achieved. Actually, we tested the kind of instruction to make this pattern by computer simulation before. So we are convinced that the simple set of the rule could be generate sufficiently randomized pattern to meet static standard, and we just asked local builders to follow these instructions. Then result was a kind of algorithmic construction process carried out with manual labor. It was an unexpected rise. We found that the finish was even better than we planned because all the lighting fixtures were nicely found between lever unit. This was done based on the local builder's idea without any suggestions from our side. This was impressive because it may not have happened if we had specified the complete pattern in drawing. This express gives an insight that in construction, algorithmic process using irregular pattern have the potential to add some more adaptability for the craftsman. So this is what we tried to illustrate on the lack of digital construction comparison of the digital and the industrial architecture. Industrial architecture based on the standardization, which is supported by machine construction, mass production, and the organization. If so, I think we can explain the digital architecture using a digital geometry, digital fabrication, and maybe it's a digital construction. So we need to think about what is the digital construction. Anyway, it should go to the non-standardization. And the biggest difference between them must be the rectangular regular form, the organic form. It's okay. However, the more big question is what's for this organic form achieved by non-standardization? Just a matter of the potential. So we to thinking about what is a novel value which created by this kind of organic form. or non-standardized form or randomized pattern. Since we have some other social demands and requests on sustainability, resiliency, adaptability, I think that we have to connect our idea to that kind of issues. So anyway, as a result, because of that background, one idea came up to our mind that if the steel was a most representative material, symbolic material in 20th century architecture with mass production, maybe we can start over 21st century architecture with digital form by using wood as another symbolic material. Because in many terms, like in performance or in the resource time or logistics time, duality, pattern, geometry, process, all of these are quite opposite in these means. But these materials, of course, can be processed easily without centralizing production. Also, using a fluctuation in the natural material can be managed with the digital processing. The individual properties of it. So, as a result, timber can be handled with relatively smaller power in the construction. So it is right way as well. It's not the wood, but in this case, we use timber. We also met a very interesting case because of one of my students being a very secure project using digital construction in a small remote island in Japan. Before it's a super rural area with reinforced concrete shell. You may know Yakushima World Heritage Site. This island is one more hop from Yakushima. Was by boat. And, it's a volcano island. Of course, it's weak in infrastructure. We can even volcano upsing while we are doing our function. Dangerous. Habitats still wrap their hometown. The challenge for their life. That is why we decided to build a shelter for them by using an on-site material without any skill. The student volunteered, no machine. How can innovate a building without a massive and labor productivity of the factory? We use wood because wood is everywhere. And wood is a very naturally easily made. So we just thought that this concrete shell are easily made by using bamboo as a reinforcement and as a scaffolding and as a molding as well. One more important thing is that we use a digital measurement. Because even though it's not difficult to build the structure by bamboo just based on a mortar top of it, we need to ensure that how much this structure are safe enough. Normally, we try to build that as we design, but in this case, we turn over process in the opposite way. We just scan the result of the construction after we built it. And I used very simple and cheap scalar and computational model. So in that case, the computational model has a certain requirement to very easy to be adjusted in the difference between the reality and the original design. So we keep on comparing scanner model and the reality and back to the digital model. Then of course, we need to resolve another issue like how all of the bamboo tree has to be geodesic curvature because it's as a material, it cannot be bended in the two way. So it has to be in the geodesic curvature. Also checking a structural status and under construction. Actually, it's checking during the construction. And as a result, all of these synchronization of the construction model has started to that we needed. So it's a little different from normal idea of the design to action, design to construction. It's almost like the interaction between design and construction. And we also start understanding that is not only happens to me when we are looking at our history of Japanese traditional timber structure. Japan wood were almost kind of sole material for building from the ancient times. And, it is wood against an intense humidity and all year and against an earthquake. Wood buildings were referred to the stone and brick building. It is open in the nature and the construction, while the Western building is private and self-standard. Well, that also goes back to our cultural space by the point that you may know this shrine is a shrine, is one of the headquarter shrine in Japan, the very famous one, and you can see it looks like a twin building. One is very new and the other is very old. But actually, this only happened in every 20 years. After one have already done, another older one will be taken down, and it is kind of 20 years cycle of renewal. It has already done 62 times. That means more than around 1,300 years. This regular renewal. Until the local craftsmen are asked together from all around Japan and participate in this headquarters into the. It's quite a ceremonial event among the community. We share culture, use skills, craftsmen. So I can say it is a kind of the schooling system, the way of the age, build a building technique, the passing a building technique from one generation to the next generation. That is why it's a 20 years divide. So I think that this kind of culture are connected with very important to me for our idea and also connected to the tectonics such as joinery, which prioritize disassemblability of all of the units. So, must be resulted in a kind of algorithmic manner of assembly involving in intersecting joints by cutting sections for each part of multiple interlocking bracket. See, all parts are unique in shape and material because of the heterogeneous nature of it. This algorithmic method, I think, you can call. And how each unique shape was made and led to the production of the considerable large building without a blueprint. So, in a sense, similar to my experience in China, most of value of the joinery are basically automatically determine their shape automatically. So these also reminds us the kind of biotic approach with the Japanese tradition, which stated in a manifest called Metabolism, 1960. And yeah, my teacher, Fumihiko Maki, was one of the member of the metabolism, saying that he's not driver of the metabolism. Anyway, it was in 1960, just around the time I born. Well, they basically stated that planism could not include a kind of self-organizing system for growth. On the contrary, traditional Japanese architecture process allowed the whole system to grow, produce, maintain the structure, respond to the environment. Research in Japanese traditional architecture in terms of the adaptability, function, and scale, whether computer simulation and the knowledge of a complex science was not advanced enough to implement it in 1960. It is now easier to, I think, explore metabolism with digital technology, applying parametric geometry for tonic system of architecture. Because we can use non-linear simulation of the heterogeneous structures. We can also apply computing power to simulate and ensure the effect of metabolism and abundant number of units. So, in that way, this is our idea of the revival of the Japanese metabolism in the digital age. Regarding that, there's once we started to study on the computational model, we call the digital wood block project since 2010. We addressed an issue to demonstrate the concept in the beginning of the stage of the project in 2010. This is what we proposed in architectural design for 7-story commercial use building in Tokyo. The model, every small wood block unit was identified with computationally coordinated. One of the advantages of timber as a construction material is on-site workability. Important usability characteristics should be gained in computational assistance now of the construction. So, by doing so, even after starting using human activities are changing, over time, but especially for the commercial use. It is an advantage in terms of the usability. The material can be modified, adapted by users themselves, professional service or major reconstruction. Why we focus on the method of the computational modularity to organize a complete structure based on the local condition. The result, a proposal shift its target to the computational model with an interface called the module navigator. To enable human-computer interaction in the process of the construction, using a good blocks to allow endless communication between the human and computer. In our proposal, also can show potential of the recycling model, the adaptability in architecture, while maintaining the structural assistance. So after we show that model, the most typical criticism to that idea was unnecessary human network manage unique parts. The complex layout excess the human ability to recognize the difference of parts and memorize all relative location spots. That seems quite a common issue of many projects and assembly with the unique parts, and also relevant issue in management of the heterogeneous materiality. Our study moves to more technical terms to realize module navigator to guide, assist human work, non-standardized construction. Most fundamental technology to achieve our ideal system is identify all modules in a real space and get precise information, the current status, such as the location and the layout of the module. Adding to this point, also to provide information to support manual work during the construction process due to the difficulty of handling enormous amount unit. Is a typical problem that the human being needs more guidance and the information, and have to work on the massive unique module simply because they can't figure out uniqueness and the intricate combination module. You can see this has all unique block has RFID each joinery positions by referring to the ID in the database builder. You can get the stored information parts. The through AR, you can feedback that information to Optima immediately. Human builders can get the feedback with some suggestions. Originally, our system developed for providing a kind of information on unique parts for humans to guide the collective action. So we is compared to kind of jigsaw puzzle where the parts themselves there's an answer. However, during the development, we found the necessity of the feedback from the current status of the physical model to computer model, keep synchronicity of them. And additionally, we found that the capacity of the computational model to adapt to human errors for intuitive decisions, the real process, relies on the result of the human work in state and brought feedback to the computational model and the overall plan accordingly. It is compared to the something assembly work with the route navigation system because it is keep on updating the guidance information. When we understanding the same system for the dynamic updating the computational model leads to the development of the further system. It's a high level recommendation based on the simulations, predicting a problem, complex status, such as a physical balance, all of them. With that idea, so we finally started thinking this stage of the system should be compared to a complex Jenga game made with a computer. Human builders are at all intuitive. One of the company interested to our critical approach, then they bring another project to us. It's a kind of deconstruction or restoration of the traditional architecture using digital construction. Regarding civil construction, this ecological approach, tradition and the novel method of digital innovation to be able to solve this issue in a different way. You could set this as a research project working in a start aiding system with the interactive data management or intricate timber modularity traditional building integration project. And you may know non-homogeneous area of course. That is why woodworking is a kind of management, traditional woodwork, kind of management of heterogeneous nature. It's even different. Inside the timber and the timber or whatever. Basic engineering strategy of the modern industrial products oriented to best constant quality by minimizing the tolerance of property such as size, strength, and weight, that we can ensure that expected performance of the design predictable by manipulating its physical behavior enough accuracy. Contrary to them, traditional craftsmen of the timber works seems like having a different idea to obtain a certain performance through more comprehensive knowledge and the specific use of visual material. Watch the forest. Timber camp is an ancient craftsman. Typically tips to tell that if you need to know about the future status of timber you're going to use, you must know about the status, growth, its unique character. So in this particular case, they use the timbers in a synthetic manner, considering the uniqueness and the non-uniformity that needs to be adapted to diversity of architectural elements or crafting processes. Traditional technology of Japanese timber architecture was built in a careful manner in the natural uniqueness and the use of material. We could test this the beam, which originally take this naturally log as a part of the structure. So then information systems to maintain traditional craftsmen. We try to make interaction between the material processing and the digital design. This phenomenon is well connected to the material engineering, the homogeneous quality, standardized condition, as well as methodical strategy to align identical rectangular module in orthogonal coordination I have already mentioned. Then natural timber becomes an inferior material, such as steel, at that point. More, it is inflammability, the aging process taken as an vulnerability to them. As a result, the so-called engineering products such as the laminated lumber, plywood are invented to get better material uniformity, productivity. Though we still keep some amount of the traditional craftsmen working on conservation or restoration of the historical buildings such as temple or shrine in Japan, the number of the craftsmen is decreasing. And the succession of the skill and knowledge can be cut gradually. That is why we finally obtained the technology to manage this huge amount of information systemically, computation, and we would like to apply it. This is the curve wall beam I went to number processing site. The bending rod form of these two is chosen for research because it seems to be the most typical example of this topic. Think of the bending rod naturally happens when trees grow in a steep mountain. The curvature is unique every single tree. Our research is focused on the subject about development of interactive cross action support system without smarter use of the entire process from original rock to recycled ones. Show that the movie it's in Japanese. So basically an intelligent path recognition technology to identify and digitize its property information for collecting in a individual material data massively and continuously in the whole history of the life of the parts, starting from the harvesting tree in the mountain to the continuous recycled processing. That is our idea. Then, to do so, we also understand a kind of metadata representation of shape and the layouts of the material to manipulate discoverability and the resolution of each part of the database. Let's say that it's a kind of database, but even if we can scan the overall, if we keep that all of the data inside the database, it is too much. It is too difficult to manipulate. So that is why we try to make a kind of way to load down the resolution of the data. To start. In a practical stage, you have a quick response for fast data and not special in the use of the extend options and the examine matching of it into the view. It is a complex issue to keep a perfect unique identification of the parts and the record all of the divisions is the process of communication and recycle in the life of material. But anyway, we have implemented this through the data mining technology. That also the other argument done by Mr. Mario about grouping the alphabet and the algorithm. In the lessons time, there was some other invention of the architectural design as an identical copy of the graphic world. Essentially. Also change the dogma functional process of the physical creation as an interactive relation between the virtual model and the real world. That also means that separate two worlds, static drawing and real world. Now we have another chance to mix it in again. So we show that one more video. We start working on that augmented reality as an experience in design of the digitally augmented platform. We decided to limit this mixed reality, especially like in the Microsoft HoloLens is an hologram. Basically, it can show the 3D images in the vision to see through the HMD matching to the presentation of the real object. So in this case, we just create a kind of guidance, 3D guidance technology to assemble so-called Kumiki puzzle, joinery toy-like puzzle. So you can see how easily you can. So we have tested that anyone can solve this joinery if we can provide this mixed reality to it. Into this. I showed you another project similar to that. In this case, no. We call it a smart giant block. Basically, we also against we are using a mixed reality, but we didn't try to build full-size mock-up like things. I think as a unit against them. But it's also synchronized into the digital model. It's a kind of mixed reality process of the physical assembly and the virtual assembly. So regarding the progress of these technologies from the built environment, consider the architecture system, which was continuous human interaction. The process must be quite important. So that is why it's required to make this interaction between the human and the digital environment. Human and a computer may not have a final goal. The result of the construction are typically not unconditional. Continuous interaction between them. As a result, it approaches a kind of collaborative process with the computer. It is remarkable if the informative support of the module in the construction. It's not more interaction from the human variables, but it shows a phenomenon of an integration of design and production. We walk through videos of here, particularly bearing this argument of the ad hoc craftsmanship in our mind. We have been working on the development of the conceptual model to let the potential collaboration coordination with human and the robot in the series of workshops named Timber Science. On the basis of these considerations, we need to set an appropriate geometric system to allow us to build a structure with unpredictable complexity, mathematical reality, enough diversity, and sudden relevancy to practical construction. So that is why our selection was this cuboid bar-like beam connected with a B angle. One of the rectangular surface attached and can be simply materialized by bow difference, like long rocket. However, once it has an B angle connection, it becomes possible to create enormous variation of form within the limit parameters and simple coordination. So we also use a kind of genetic algorithm to find the solution in assumed condition. It is not always able to find out if it is a module of two units connected in specified angle, and the shift is when it is successful. So then two-unit module becomes a correct, which is to connect the two specified surface. At this point, computational order has a vast advantage for the rapidness and the accuracy. So we are keep on doing the similar workshop about 3 times. Sure. Okay, I got it. Then maybe should I just go right up. So, right. Then comprehensive innovation in digital activation gives us a great chance to accurate all of these: the communication, the computation, and materialization, the adaptation. So not only that using an algorithm for design, but also using more things. It's frequently solve a lot of issues. As a wrap up, I will back to the some practicing work of my work and again using a CA. This was a competition scale. Unfortunately, we couldn't do more in this case. But, later on, we could get another client to try the similar idea again to the different project. I will skip this, but anyway, just for screen, but there is a lot of technical issues, like how we can cut the all of the sun, direct sunshine into the roof, or we also need to take this as a structural part resisting wind force and the seismic wave as well. And also we have to solve the something like how we can lay it down, or how we can push the window cleaner inside. All these are tested in 3D models. So likewise, we can apply all of these ideas back to the gradually back to the practice. This is what we are doing, and thank you very much. That's all. Yeah.
Thank you, Professor Ikeda. We will hold the questions because people are watching on YouTube, and then we will have a panel discussion after the next presentation, which is Professor Tom Kavan. The first two lectures were really about computational artifacts and in design. So Rob spoke about the design of software systems and design space exploration, and Professor Ikeda talked about making of artifacts, whether at small scale, architectural scale. And now we'll move on to Professor Tom Kavan, who will speak about smart cities and the use of data and design at a much larger scale. And perhaps he will also wrap up around the big ideas around design and data science and where it's all going from a pedagogical perspective. And he might illuminate us a little bit more about his thinking around these topics. So over to you, Tom.
Slideshow. Thank you very much for Professor Ikeda to take us through attitudes to design and design theory, interface design. The connection back to traditional kind of instruction, use of data in reconstruction. Seeking to show my I failed to do so. Failing. Shared. As you go, I've got you to share my screen first.
Yeah, we are.
I'm missing something. Let's talk. Use
No, I can't. And I
from
can't.
Rob.
I don't know his number.
For theory A, about how this might be explored, understand how a smart city use data design. But I then Rob Woodbury's theory B, to start thinking about the elements talk to each other. And I came to this view of the world. I'll talk about urban data, not about cities, but these will be a design view with urban data. Australia is distinctive, unique in the world, so for a national infrastructure which shares urban data. This was a project that I started in 2010, a federally funded project to support urban research across the nation, make data available for urban research. The central element of this is that the data that's useful for urban research is not generated in one place and held by one authority. There are currently today over 5,000 500 data sets available in ARM. The data set available in ARM, there are thousands of views. The use is very heterogeneous, and the data sets need to be maintained. The only way to maintain them is to ensure that data generators look after their data and continue to make it of value. And therefore, is a federated data set data portal to these thousands of data sets. ORAN has to manage the harmonization of data so that different data sets can be used in a comparative way, but most importantly, to harmonize the access to them and to maintain a metadata system which allows for data discovery in a consistent manner. So offers, on the right-hand side of this image, a workbench with a series of tools which allow people to manipulate data. So, for example, you can get access to proper data, but then you can examine that with a different data set held by a different a different authority, and look at affordability of housing. And indeed, you can drill down to find out which parts of the country are at risk as mortgages rise and wages don't. You can use it for examining productivity and the co-location of different functions, for example. Also then use it with these data with a series of tools to examine neighborhoods, drill down to specific questions, which streets allow for pedestrian access, and within a set amount of time, say 15 or 20 minutes, how far can you walk and be accommodated? This has been used to look at the location of railway stations and transportation hubs to see how they map onto neighborhoods. Data can also be overlaid onto data accessed through satellite photographs. For example, tracing pavement layouts and tree locations, and therefore working out which neighborhoods are comfortable to work in and which are not. You can examine the city and find out which parts of the city have reasonable access to public transportation, and you can then overlay those onto work opportunities, education opportunities, and begin to analyze the livability of the city. So far, this hasn't really touched upon design. Examining a neighborhood and looking at land use and the potential of that land for different applications would allow you to play out scenarios. This is a tool that was in fact developed by Swinburne, Curtin, University of Melbourne, and Canterbury to allow for the land use planners in particular, in this case, to examine potential for various land uses. That's open data and what we're able to do today. Let's then go to smart cities. It's a bit hard to describe. Open data I can describe in a fairly factual way and talk about the data that's supplied and available and how you might use it there. Smart cities are a bit of a conundrum. The question that comes to my mind is, how do we read a city? Look at this image on the right-hand side. You read the bottom of it, presumably, the Festival of China. Those of you who have knowledge of Chinese script or kanji can read the top line. And read the yellow thing in the middle. Quickly you'll find that top yellow object, it is the word the, D-A-T. The Roman characters are laid out according to a Chinese graphic eye. This is the work of a Chinese artist called Shibin. He's playing with your mind, making you read space, graphic page, differently. I'm bothered to understand the words here on the screen. It is the beginning of an essay that you can buy offline, online, and it's an essay about a city. What I'm trying to get you to see here is that text describes the city in a linear way. You start from left, you work your way to the right to the top line, you go to the second line, left, right, and then you go down the page. Also is an underlying principle, one of the most common approaches to urban design, which is popularized by Kevin Lynch, an author in the middle of the last century, influential in our understanding of the city. And he broke the city down into how we read it visually. Described the path, the edge, node, landmark, and the district as being ways to compose a city. These are linear. They're just like the script we read in the English language, left to right, line by line. Faced with something, a script like this, and you wonder, how can I read that? Well, if you understand the characters, you can start composing different meanings. The word construction, the word architecture. In other words, you can read from left to right or right to left. You can read from top to bottom or bottom to top. So, repeat character is not only left, right, up and down, but on the diagonal, a multiplicity of meanings, 10 in all, and probably 12. That for 4 characters. The permutations in these 4 characters allow for a large number of meanings. Yet, read the city, it doesn't allow for a large number of meanings. We're looking at this image. Lynch described a city as a series of moments, visual moments that we chain together rather like beads in a thread. You look at this city, suburb, you read it as a 2-dimensional mat. There is a series of moments that can be chained together as experiences. Those aren't the only ways to think about a city. Cities are not 2-dimensional. Cities such as this, which of course is Hong Kong, is far from 2-dimensional. People would read that as what I would call in computational terms as 2.5-dimensional. It's a 2-dimensional city extruded vertical. When you start breaking down Hong Kong into the way that buildings are interconnected and the spaces are interconnected, only space geometrically, but in time, you realize that Hong Kong is not 2 or 2.5 or even 3-dimensional. It's a 4-dimensional city. That was a subject of the book that I mentioned earlier, making Hong Kong from vertical to volumetric. And it was what I wanted to introduce there then. Cities are to be on the design sense as volumetric components, not as positions of elements, objects, nor compositions in 3-dimensional space. As we're examining smart cities, is why do we have cities? This image eloquently portrays, initially, aggregation of people around sources of energy and sources of raw materials. And as energy became just independently movable, transportable, coal or oil, then cities started to move away from energy sources and move to resource centers or accessibility centers. In Australia, most large cities are resource located. That is, they are located where fresh water was available, accessible when you sailed up the river from the sea. Today, cities are much more than that. Cities today are locations shared intellect, shared innovation. That's why people come together. That's one of the reasons that working from home for everybody doesn't really work, because we need to have social engagement to generate new ideas. Cities can be expanded. The United Nations has identified their sustainability goals and number 11 are sustainable and cities and communities. Yet cities are the vehicle for attaining 17 goals as a whole. In Europe, they identify different purposes for cities, but in none of these descriptions of cities are cities simply collections of objects, buildings, gardens. They are there for purposes. This leads to a fracture with the theory of smart cities and the difficulty that designers have with smart cities as a concept today. Smart cities have been defined as a field largely by engineering professions, and they look at cities as a collision of systems. Think of the various elements of a city, the functions of it, isolate each of them. The energy provision, the provision of services, the inflow of materials and resources, the outflow of waste. Smart cities are created by addressing each of these subsystems. Each subsystem then gets optimized. So you get the most efficient centralized energy production and distribution system, most efficient distribution of food, most efficient mobility system. Cities then become a collation of these optimized systems. On the right, you can see an example of that. There's the competing systems effectively begun to destroy the quality of a city that we, as inhabitants, look for. Cities are more than assembly efficient of systems. Are neighborhoods, and they are places that we live. This image of Seoul in Korea, some major neighborhoods identified. Next, we think about cities, therefore, not as systems, homogeneous networks of one, an overlay of interrelated networks, heterogeneous networks perhaps, which allow you to start building neighborhoods and differentiate characters from one from the other. That leads then to the perception that cities are indeed complex. Therefore, as complex systems, they need to be understood as interacting systems. You have therefore to move beyond optimized subsystems to systems that best fit and allow for the abilities and the opportunities of the adjacent systems. Challenge here, though, for a smart city. Smart means learning. If cities are indeed to be smart, to be cities that learn. So, where do we head with this? We are currently working that cities have to be considered as complex adaptive systems. Complex because the overlay of simple systems does not adequately describe interactions within us. They have to be adaptive. Cities evolve and accommodate unexpected activities. Adaptive cities allow for emergent opportunities. Simplicity to be replaced by systems that allow respond to the contingencies of experience. Cities, therefore, in this frame of mind, are cultural constructs. They are not geometric or technological constraints. The engineering, therefore, of a smart city cannot dominate the direction of the city. It has to support the complexity and the adaptive behaviors of a city. Cities are not static and they're not predictable. It's a very high-speed introduction to the topic. They start saying smart cities use design data. What are cities? We can see with them. How do they allow for design to allow for emergent behaviors? So, end here with significant challenges for urban data. Take what I said at the beginning. Cities are a rich relation of all sorts of things. Extend that notion, everything therefore is open. You have to consider all of your systems, the water, where it comes from, power, where it comes from, where does the food come from, where do the people come from, where do they go, where does the waste go. Boundaries can't be drawn around a city. Everything is open. Second aspect points to the sources of data. As with Oren, we have currently 5,500 data sets. Those are simply the ones we've managed to wrestle in gaining access to. Authoritative data versus available data. Get the data from power sources or power companies and understand how much energy is being used. There are new sources of data. Every modern car has a range of sensors on it. They are broadcasting data constantly. Twitter is broadcasting a stream of data. Every other social media is. The location of every handset as it walks around your pocket is broadcasting data of location. These are used in different ways, but we draw a distinction between between authoritative data and available data. What is available may not be reliable. And the differences between these data sets, maybe they can't be mapped and overlaid onto one another in a sensible way. The side that is into something. Which data do you really need? You've got data which is being streamed like sensors on cars. How often do you need to have those data? You're working with census data, demographic data. You have the intervals established by the government, and every 10 years you get a sample. You overlay a 10-year sample to 10-second sample. There's great challenges there in using data in a city, in a context, is to sort out the difference between coincidence and causation. Not allowing inference to drive you when you're designing something. I think that if you can manipulate one aspect, one parameter, and then direct the outcome of a different one. So I go on through the following, the rest of the contextualization, trying to understand what all these data sets mean in the context that you're using them. Very large issue, ethics and security, because sourcing data on cities and then feeding it and using it for other purposes is quite unethical. If, for example, you're driving or controlling speed lighting in a smart city, try to minimize energy use, what's the right now? In a particular neighborhood, like there's license turn them on and off. Is it based upon need? Is it based upon neighborhood wealth? Is it based upon economic value of that neighborhood? You just turn all the lights on and leave them on all the time, because that's the simplest answer to a difficult question. The last question is the hard one. It's just dynamic. You have data about a city that tells you what things, whether the time dislocation is nanoseconds car just went by, or its demographic data is 10 years or 9 years out of date because the next census has not yet been conducted. So you don't really know how many people live in the neighborhood that you want to design for. The real challenge, of course, is that design is always conjectural forward. Designing for 10 years hence. What value is data from 10 years past? Designing something for 10 years hence. A very quick high-speed tour through questions of smart cities, design. I've raised more questions. So that's intent. And provoke.
Thank you, Tom. Can you hear me? Excellent.
Okay.
Thank you very much. So that was a very concise presentation, which leaves us very conveniently time for a panel discussion. And I'm just trying to figure out how best to conduct it. Is Rob there? Rob?
I am indeed.
Okay, great. Thank you, Rob. Ikeda, are you there?
I'm here.
Okay. The idea is now to have an interactive discussion around the three topics, which had a lot of content from very different areas. And it goes from what Rob was saying about the design of software systems and how do we actually bring dialogue between design and data. And then your work as well, with how do you bring the material aspects of design and then combine that with artifacts and multiple scales. And then Tom's overview of smart cities and role of design, and particularly big questions around data stores like RM. How do you bring design into this whole mix of cities? So if I can start with you, because you're sitting in the middle and you're the architect, I guess, all three. Could you elaborate a little bit on Rob's presentation and Tom's presentation of where you're sitting? And then I'll do the same with the others.
Me?
Yes.
Oh yes, it's a very difficult question, but actually I really understand what Professor Rose is addressing. That is maybe biggest base of what is a design meaning for human being. So maybe now that is becoming another question. Used to be people just think maybe design is more easily called theory B. It's happening only in now intelligence to make a design is in between computer and human, or in between data and the human. That is, I think, a big change for me. So even the case of my case, the materiality. If the materiality doesn't have that, we don't care about it. But since material also has a huge amount of the information which we can deal with in computational way. That is what uniqueness, something like the uniqueness of the materiality, not the wood, become an issue. Same user, the human user also, that can be taken as amount of data. So maybe the meaning of design is the interaction between human and the data, or human and the artificial intelligence, human and the computation. This is what I started thinking of. It could be the answer to you.
Well, I guess yes, I understand that, this whole notion of data and the human and dialogue between humans and machines. I'm also interested to know, how do you see the education of new designers, if you like? And this is a problem we face all the time. The traditional design disciplines of how they're structured and the new, technologies that are coming on board, the new ways of thinking, and how do you train new designers?
Well, that's another good question. That is why I'm recently working on organizing a new academic group which called architectural informatics. Because current architectural academics are orthodoxically established in a very long history of what the architecture is. Now the computer have not two, maybe it's much more than two, as everybody knows. Some billions like informatics, which in the world as a and the mechanism of the data flow must be important, as Professor Thomas Kuhn, I think, addressed. How we can perceive everything as data is one, or everything as a information flow or information system. The one most critical point to think about it. So that's why it's very important. It is not about the picture education. This fundamental perception of informatics needs to be educated maybe from the primary level, primary school, secondary school, the high school. Maybe if they have enough idea of what is the perception of the informative world is established in our vision, then I think it's more easy to put what is an architecture on top of it. Currently, since we are, undergoing situation, so unfortunately, even the new generation are not well educated in that way. I also think that since materiality or physicality or kind of body environment is another biggest nature of architecture. We should not forget about that too. It's a matter that how we can take that important part or keep that part is and change the viewpoint looking at. So it is not an easy idea, or I don't have a super clear solution yet. But, maybe in near future we need to answer this, and because industrial sector really require this kind of interaction anyway. We want to someone who can deal with everything onto the idea of how they can process the data. Even it's an architecture, even it's an urban design.
Thank you, Professor Ikeda. Thank you for your contribution. I'll move on to Rob now. sort of doing it in the reverse direction. And Professor Ikeda mentioned that materiality is going to be very big, should be a very central condition of dialogue between human and machine. Of course, you've talked about the abstract artifact and talked about going away from the single document idea collections in order to be able to handle the complexity of the design process. So I wanted to ask you to elaborate a little bit more on how maybe the training of new designers, will be impacted by these tools, and vice versa. How, if we have more informatics, as Ikeda-san said, right from the primary school level, would that impact the creation of human-machine interfaces?
That, Shamit, is a difficult question. And faced with a difficult question, you spin your own answer. I look at architectural education, and from the time I was a student in the early 70s until now, I see patterns and some really wonderful things, but I also have some questions. One of the things I see in Professor Ikeda's presentation is an engagement with materiality through technology that just brings into the realm of possibility some things that we could only talk about a generation ago. It brings an engagement with materiality that takes it out of motherhood and apple pie statements like know your materials, and here's a brick that's in the architecture school library. Direct engagement with materials, assemblies large and small, enable a very different kind of learning than we can get out of books or by laboriously drawing configurations and material. I think that must be wonderfully freeing for students. That's entirely good, that there's a enablement of kind of a ludic or playful interaction with materiality that just wasn't there before. I think in your question is something disturbing. And it's too easy to focus on what technology may or may not do for education. That may take us away from some super important questions of value. I think we've done an equally poor job of in architectural education. There are existential issues of today. The sustainability is a big word with many, many meanings. But for architects, it involves views of buildings and cities as integral part of systems that must be circular, that must break out of capitalist growth, that must be part of a steady state economy in a finite world in the future. So those are questions I think we absolutely need to ask. I think a more important question is how can technology help us ask those essentially ethical questions? So to me, that's a larger challenge. We have absolutely marvelous tools for inquiry now we did not have in my time. We have students who are arguably less skilled than the students a generation ago, because many things are in a way too easy. Are we asking the right questions?
Well, I have a question from the viewers from YouTube, and it actually feeds very much into that answer that you've just given. The open question for you is is there a push to train students in higher computer languages to create tools, or for experts to create tools to enhance education?
Robert H. wrote a series of very, very nice articles that can be summarized as first build your tools. And From the advent of explicit symbols in architectural representation, or digital symbols, there's always been an undercurrent of build your own tools, manipulate your own symbols, do your own thing. It's been one of the most marvelous parts of being in computational design and architecture. And like elements of parametric design, things like the Smart Geometry series, things like Fabricate, are all encouraging that level of computational sophistication in every learner in architecture. On the other hand, and people who are fundamentally designers and fundamental interest in learning about design build every tool, conceive of and build every tool that they need. And I think I hope I've made a compelling argument today that for some tools it just takes many, many years to develop the conception of what the new tool should be. So there's a deep place for expertise as well. But there's this marvelous middle ground that I think is exemplified by people like Brady Peters and many others. And that's that some designers become sophisticated enough as both designers and symbol manipulators to start making new things that aren't engendered by the commercial tools in front of them, and that aren't possible without practice for some sort of symbolic tool that pushes practice forward. And those people do really interesting things in the world. So I evaded your question again.
That's fine. It's as fair an answer as we'll get. I'll move on to Professor Ikeda. Thank you, Rob, for your patience and your talk and also taking questions from the panel. I will move on to Professor Ikeda because there is 2 questions here I'm reading on my YouTube thing. On the glove device, what is the glove device in the digital woodblock photo, and what interface is it achieving? And a related question to that is regarding the training using augmented reality. Does Professor Ikeda have any data on how much of an improvement augmented reality provides over other training methods?
Okay, well, about a first question, basically, our first model of this data globe, it's just to collect the ID number of each node of timber joint. And by touching the node when we are building, the data goes back to the model and it's automatically back to the digital model. So basically, it is a kind of tools to synchronize the reality of assembly work and human being back to the real model. That was the first version. In the second version, we are not using data globe anymore. Using a so-called QR marker, which is something like a 2D barcodes sort of things, which I can correct more easily about the location. Of course, it is not perfect to precise, but since in our case, the connection between the unit have already determined by another model, so it is not so difficult. So for the second question, I think, augmented reality can easily give us the idea. So for the target location, because we can view kind of vision which is showing the target location which they things to be. On the other hand, when we are creating a virtual model, more rapidly or interactively using it, it will change the speed of intuitive understanding of the human being as well. We have not measured the size effect of it, but we convincing that anyway that is one of the effects of the human being. So, in other words, this intuitive interaction of the human being will be enhanced by that kind of tools.
Thank you, Professor Ikeda. I think I will move on now to Professor Kavan to wrap up. We have 10 minutes. And Tom, are you there?
Yeah.
Excellent. I wanted to ask you the same question that was given to Rob because it was an open question for the panel. And it says, is there a push to train students in design, presumably in higher computer languages? And do design students need to create tools, or do we train experts to create tools that can enhance design education? I'd like to add a second corollary to that, knowing that you're heading into a new adventure soon, on the role of data and data sciences in design education. How do you see the future? If you could just wrap that up, it would be a nice end to the workshop.
Two very interesting. First question, do we rely on experts to design tools or the students design tools? Looking at one of the dimensions of tools which appear in the digital world, which haven't appeared in the analog. If someone designs a hammer, they're essentially working with physics of force and moments to create something which can hammer in a nail. When you start designing digital tools, wittingly, you are drawing upon a huge work of cultural assumptions of how you work, what you want to attain. Those cultural assumptions are implicit, they're never made explicit. For example, in my talk, I talked about how cities are considered to be two-dimensional and linear. That leads us to assumptions about what kinds of things we can create to analyze cities and city modeling. Cities are principally then three-dimensional. We create different sets of tools, but we don't have to. These tools applies to two-dimensional, three-dimensional models. The further commenting in art and design is that you draw. Well, those drawing systems have layers. Why? Layers appeared in the 1970s as a way of managing clear acetate overlays where you applied ink to a plastic. You created complex drawings by adding another layer of plastic so you can see through it, adding lines. Yet now it's encoded in software. Go back in history of software, you look at the building design system in Oxford in the early 60s, mid-60s. It was an object-based design system. One came layers in the 70s and wiped out this concept objects, and then later rediscovered. You've got experts designing tools, bringing in their assumptions about how we should represent things, and not making a tick. Then users struggling to work with these and assuming these are natural conventions. Another one is fly-throughs. Why do we have fly-throughs? It's an assumption built into the first three-dimensional visualization tools and how you move through space. They come basically from Hollywood, gantry, the crane, the dolly. So I'll go with Rob's answer, which is that users should design their own tool. They know what they want and impose their own cultural assumptions. However, all users are skilled enough to first recognize the assumptions that are trapped within. And second, they're skilled enough to build their own. So inevitably, it comes back to experts. If you want robust systems that can be shared by a large number of people, which is what you have to have, you don't want everyone having their own tool. Or you come back to experts. Those experts have to be far better at understanding the conditions within which they're trapped and how they're working. Then on to the role of data, the same things apply there. So I'll leave that to your own imagination, thinking that one through. But there's a different aspect I'd like to talk about in the role of data. We have come to understand that data is powerful. Parametric systems, for example, allow us to manipulate design through manipulation of data. Therefore, we'll control the parameters that are being affected and the outcomes. Trying to understand that, we begin to think about the types of data and the sources of it. At the same time that we're working our way through that problem, the sources of data is exploding. Suddenly, everything has metrics applied to it, or sectors, or kinds of data generation systems, and we have more data than we can cope with. So you've got the situation we're beginning from, where data plays a role. On the other side, there's much data. So we are faced with the real challenge, filtering and reducing again. And that is always a design question. That's what designers do all the time. We are very selective in our attention, tend to certain things that we think are most important. That's what we need to start doing with data and learning how to do that. Much of our previous training in education in design has been to try through tacit means to inculcate people to understanding what is important. It changes from one time to another. At some earlier in your careers, you attend to ergonomics, human dimensions, you size something about what a hand grasps, so that's comfortable within a hand. Later, you then move through other kinds of sensors and start designing for those too. They're all data. The role of data is going to become much more important. Only as we get people to start filtering the data they attend to and to be working out which data is important and why is it important, and therefore how it can be used. At the moment, I think our tools for doing that are fairly crude and fairly rudimentary. We must expand them. Earlier on, you asked a question around what are the frameworks training for design. For example, in industrial design, it moved 10 years ago. It was to move towards human-centric design, away from process-centric and material-centric, human-centered. I think we have to move past that now. We're at the point where, in some ways echoing what Rob was saying, we have to move to a textually centric, eco-centric, and environmental-centric. It's no longer human-centric. So this notion of cradle to cradle is just after that in a way. But a lot of what here was showing, in particular with the timber work, we make rectangular timber beams because we can describe them. Then we force a tree to generate a timber beam that's rectangular. But now we can read the grain of a branch, and we can turn that by algorithm into a milling system because it's a structural performance, a non-rectilinear beam that's in that timber. Like Michelangelo's, you can see the sculpture in the marble. We're beginning to see the beam in that wonderfully contorted piece of timber. That's data.
Can I add one more word before ending?
Yes, please go ahead.
Yeah, most typical question for me after I showed some robotic work or some computational design, people normally ask me, what kind of the role or remain for human being in the end after robot can do everything? So my answer is quite simple. There is one important thing is robot cannot do or computer cannot do is robot cannot joy process. They cannot have a fun process. Pleasure, fun, joy. These are, I think, one most important human-centric issue. Even we are starting all of these digital technologies, including artificial intelligence. That is why that in our case of human-robot interactive experiment, we try to limit the use of the which they don't kill our fun, the crafting something, designing something. Craft or design or all of these should be the pleasure, should be our fun. That must be I think it's very important topic gradually. Because of the used to be, we just ask machines to do something boring. Now we have to do something boring. We accept all of these. Now also I think we need to let the student to understand and make the student to be well motivated. What is fun? What is a pleasure? What is an enjoy of crafting something or building something or designing something? Must be very important.
Thank you, Ikeda. Rob, did you want to say any last words?
Well,
The environment-centric or the context-based?
I couldn't agree more with what Ikeda just said. And I would interpret it as, against the question of what is there left for a human to do, I would say everything. The problems that we address are not tiny things. In every problem that we encounter, and we encounter almost entirely such really complex, wicked problems, understanding what the design is intended to do, where it's situated in the context. These are rich, deep, historical, cultural questions that can only be understood in the context of where we are now, cities we're surrounded by, what's going on in practice, what the issues of the day are, and those cannot be anticipated by computation. So I'll go back to my claim that the result of every oracle, every robotic process, every simulation, every forward-looking computation is the beginning of further human inquiry. I don't see computation ever changing that.
Thank you, Rob. Thank you, Professor Ikeda. Thank you, Tom, for bringing a nice note to the structure to the conversation today around environment and eco-centric design. And I think we'll have lots of things to think about. But I'm going to hand over finally to our colleagues at the Hive who are standing by, I guess. Andrew, did you want to say a few last words before we wrap up?
Thank you. Thank you, Shambit. Can you hear me? Or are we're still muted. Can we unmute that? Thank you, Shambit. Appreciate your kind words there. Very much appreciate all of our presenters' patience in our quick transition to an online presentation for this event. It was all happened very, very quickly, but we were well versed in online presentations from some of our other events here at the Hive. So. But this was a little bit more complicated. For those interested, we've been using both WebEx and also YouTube and a few other bits and pieces in between. The wonderful Hive team, who you can't see, have been busy working behind the scenes to make sure this all works smoothly. Thank you again to Yasushi